बिकॉज आई डोंट नो हाउ बट देन अपने आप वो साइज लिमिट से सेट होके अपने आप और वीडियो रुक जा रहा है बीच में. So what we are going to do is we'll go sort of fast. In the previous video we had already seen that B is equal to KQ by R, and we need to put the sign. That's important, remember. Now let's basically talk about the electric fields. The electric fields, if it's a positive it originates, and if it's negative it terminates. The electric field positive originate and negative will terminate. Electric field lines never uh, never form a closed loop. The tangent is given, but a point will have only one tangent, not more. Two lines can never intersect each other, because if that happens then there would be two tangents for one single point, which is not possible. Density of the field lines is directly proportional to the field strength. That simply means more dense, more field strength. Okay, so now basically we're going to talk about, see, if the density is here, the more dense here, the less dense here, so EA is greater than EB. The same density, so E is equal to AB. When you talk about EA vector is equal to EB vector, direction has already changed, so this sentence is false. Okay, I hope you get it. The direction of the electric field from higher potential to lower potential only. If electron is released from rest in a region of uniform electric field, it goes to high potential to low potential region. That's false, because it goes from low potential to high potential region. Why? Because you're releasing an electron, you're releasing a negative charge. When you're releasing a negative charge, it will run from the low potential, that is minus, to the high potential, that is positive. Common sense. Now we're going to talk about the relation between electric field and potential. We don't have time, so we'll not go through derivation. If you need it, just let me know, I'll post it. Electric field into dr will give us the negative of the differentiated potential. If E is constant, we have Vf minus Vi is equal to minus E dr, that's from Ri to Rf. If E is not constant, then you have Vf minus Vi is equal to integration of minus A into dr R1 Ri to Rf. Okay, so now let's talk about the equipotential surfaces, which actually means that a surface which has equal potential, that has same potential at any place. Like here, A and B, the potential VA and VB are equal to each other. We have a few properties for the equipotential surface. The electric field should be perpendicular to the equipotential surface. The electric field line cross the equipotential surface perpendicular to it. No two equipotential surfaces can intersect each other. That simply means like this. If electric field is perpendicular, it has to be perpendicular to the equipotential surface. You have a surface like this, the electric field should come like this. Electric field lines cross the equipotential surface perpendicular, it has to cross perpendicular. No two equipotential surfaces can intersect each other. Work done by electric field makes a charge, when a charge is moved from one place to another of equipotential surface is 0. Work done is delta minus delta U, that's U I minus UF, that is Vi is equal to Vf. In an equipotential surface, you have work done in electrical field is 0. The shape of the equipotential surface, due to point charge, the shape of equipotential surface is sphere. Va is equal to Vb, that is Va is greater than Vd. That's like if you see a here, a B here, a C here, and a D here, Va is equal to Vb, but Va is greater than Vd because the density is more here. That simply shows that Vb is greater than Vc. Okay. Okay, now let's come to flux. Flux is basically एक एरिया से कितना चार्ज निकल रहा है. That simply flux is E dA integrated. Okay, if E is constant, it comes out of the integration. If E is not constant, it stays inside the integration. For an open surface, we can take normal in any direction, but for a closed surface, we have to take it perpendicular or outward direction to the surface. I hope you understand it. The flux of a sphere is 0. Let's imagine a box and you have the lines crossing it. Basically, the flux inside will be equal to the flux outside. So the flux inside the box is positive and the flux outside the board is negative. Magnitude of flux through a surface of directly proportional to the number of fields crossing the surface. Flux associated with a charge, that is simply flux is equal to Q by E epsilon naught. Now we had studied that flux is equal to E into dA, right? Now if you can remember, for E we had studied that, or let's talk about first dA. Okay, fine. For E we had studied that it's 1 by 4 pi E epsilon naught, and for that is kq by r square. For dA the area is 4 pi r r square. That's where it gets cancelled out and you have q by epsilon naught as your flux for charged things. Next we have Gauss law, that comes in the very next video. Now the videos I'm just trying to make it shorter by myself. So let's talk about what all things we are going to cover before this video ends. We're going to cover the Gauss law. We even have a few shapes on which we are going to study. Okay. Then comes the topic of cavity, and then after ending cavity we have another lot of shapes we want to study. We have electric dipole, and then we have conductors. This is a hell lot chapter. We have conductors and we also have capacitors.